This talk is about a design consideration which leads to increase in the quality factor, and this is I'm presenting for my student Mohammad Asadian, and this is a collaborating effort with in my group and Tom Kane group at Center. Pretty much any vibrating mass, if it's isotropic enough, can be turned into a gyroscope. And this mass on spring type system, if it has 2 degrees of freedom, can be instrumented to operate in what is called rate mode, or device measuring angular rate of rotation and whole angle mode. So this is the rate mode and whole angle mode. In both cases, regardless in what modality the device is instrumented, the sensitivity of the device will benefit from increase in quality factor in red, and increase in symmetry or reduction in the frequency split between the principal axis of motion. Over the years, we've been exploring to go beyond a single degree of freedom mass or single mass. And the reason to go through this complexity could be very, very different. One reason to increase degrees of freedom is to increase the robustness of the overall design, make it less sensitive to variations in the temperature, variations in changing scale factor due to vibrations, as they expand, typically as the expanse of the sensitivity. The second sort of reason you may want to increase the degrees of freedom, number of degrees of freedom in the system is to increase your signal to noise ratio. And this is the amplitude amplification type idea that we're exploring under some current program. And the third reason might be dynamic balance. And the dynamic balance, the reason one wants to make a dynamically balanced structure, and I'll explain in a second what it means, dynamically balanced structure, is to reduce the interval, the energy loss from the device to the substrate. And so this is really the topic of this paper. We've been working for probably 6 to 8 years now on a quadruple mass gyroscope, and this is an example. This is an example of a successful, let's say, implementation of this dynamically balanced architecture. What we have in this design is 4 masses. They're driven intentionally in antiphase. It's like two forks which are moving in antiphase. And when z-axis rotation is applied, they respond in antiphase mode, all 4 of these masses. The way this device is designed is we have a 0 reaction force and 0 reaction torque at every attachment, at every anchor point of the structure. And by pursuing this architecture, we're able to demonstrate device operating, silicon device operating as a thermoelastic damping unit with a quality factor greater than 2 million. And the performance of this device is, for example, angular random walk is 0.015 degrees per kilowatt hour, bias stability is 0.09 degrees per hour. Their disadvantages, and this device is currently commercialized, it probably will be a product coming out of Northrop Grumman very soon. The disadvantages of this device are, it's a complex structure. There are 4 masses, there are 16 suspension elements, 12 coupling mechanisms. There is an issue of, it requires some special consideration to achieve mode ordering. So what we asked is it possible to achieve the same features of fully dynamically balanced structures by a less number of proof masses, less number of degrees of freedom in the system? And this is really the topic of this paper. Previously in 2015, transducers, and probably we have a journal paper as well, there is a patent on this, we demonstrated that it is possible to come up with minimal realization, where instead of 4 masses, 2 masses will be used. The reason we call it a Foucault pendulum or double Foucault pendulum is because if you have a single proof mass, it's sort of the dynamics of is equivalent to linearized Foucault pendulum. Pendulum. The system that we are considering is sort of can be the analogous would be 2 proof masses connected by a string. And so this is why dual Foucault pendulum. And we demonstrated that we can achieve high quality factor. From practical consideration, one disadvantage or difficulty was that the operational mode of the device is not the first structural mode of the system. So I will say in a few seconds what it means. And this is really the core of this paper basically to avoid the problem while preserving all features of the dynamically balanced structure. So if you just, in simple thinking, take two masses and you dynamically couple it, this would be the equation of in-phase mode and anti-phase mode. In frequency domain, you will have in-phase and anti-phase frequency response peaks. So the problem is the operational mode to achieve the dynamic balance would be anti-phase mode. But because of the structure, in-phase mode becomes first, and this is a problem because it results in mode coupling losses, so energy can be distributed then between the two modes, which is undesirable, instead of focusing at the mode of operation. And the second problem is the sensitivity to external vibration. So typically, the structures are designed so that they're immune to any vibration before the operating frequency. It's the order of modes is not right, so this is the problem. So we're trying to, and this is sort of links well to the overarching topic of this, is to come up with a structural design which will eliminate this problem, which will reorder the operational modes. So this is sort of a pretty neat approach, I think. So you couple the devices by a cantilever beam. Clamp cantilever beam, these are the two masses. So when there are two masses are operating in antiphase mode, the beam will buckle at its first mode. But when it's moving in phase, the beam will couple in the second mode. And because of the mode which is inside of the beam, the structure, the antiphase mode, now becomes the first mode. And the in phase becomes the second mode. So this is exactly what we're trying to achieve. We want to have as low as possible operational frequency, but we want it to be the first mode. So this is really what we implemented, some math which goes into how all the selections are made. We implemented this device, and this is where collaboration with Tom Kenny comes. We used the epitaxial process, it's actually a Teriyaki process, which I don't think they really published on the nature of this process, but the bottom line, the structure themselves are about 40 microns, and the neat part of it, it's vacuum sealed on the wafer level. So the device is sealed, and the device that we designed, and it's partially due to the limitation of the fabrication process, is less than 2 millimeters on the size. So it's a very small device, not too much capacitance, but nevertheless, and we integrated all the coupling mechanisms and all the mechanisms to accomplish this Dual Foucault Pendulum architecture at the same time. So this is experimental results showing that we achieved our objective. This is the frequency response of this Dual Foucault pendulum with the coupling system, where the first mode at 15 kilohertz is antiphase mode, and the second mode, which is in-phase mode, is at 26. So the modes are separated by 12 kilohertz, which is a very good separation for a practical device. So we achieve this mode already. Then yes, we achieved the mode ordering, but the question is, do we still have this number one objective to have high quality factor? Because the starting reason for this whole thing is to achieve the thermoelastic damping of the system. So we tested, so this is the quality factor measurements of the epitaxial device. The quality factor of this device was 127,000, which is where the thermoelastic damping was 1.51 million. So meaning that, well, we have a lot of losses, much more, very far from the thermoelastic damping. To understand what the reasons are with the design, or maybe just vacuum is not good enough in the epitaxial process, what we've done, we drilled a hole, we destroyed the vacuum cup of this vacuum package device, and put it in the vacuum chamber, and we increased the quality factor from 127,000 to 8,012. So the time decay time was increased from 2 seconds to 17 seconds. And then we said, okay, well, we can't really do much experiments while developing the vacuum chamber. We engaged our SST vacuum package process with gas activation. And we sealed it, we activated gathers after, at the day of the vacuum packaging, the quality factor was on the level of 714,000. Again, so it's increased from 127 to 740. And after 90 days, the quality factor, during 90 days, the quality factor was increasing. And after 90 days, we achieved the quality factor 1,059,000, which was really very close to 1.1 million of the thermoelastic damping. And this phenomena we published into this paper in some of our previous publications. So basically, the conclusion was we achieved both objectives: anti-occasional operation, which became number one mode in the structure, and the second objective that we achieved is we eliminated ample losses because our device was approaching the quality factor within the last decade. So on day one, we haven't done it after 90 days. On day one, we characterized the device. Remember, this is a very small device, so 2 millimeters, 1.7 millimeters in size, very low capacity, but nevertheless, as fabricated, delta F was 110 hertz. Of course, this can be improved, it's a process issue. We electrostatically tuned the device to 100 millihertz. We operated this device in open loop rate, and the only loops which we implemented is AGC and PLL. The device performed on the level of 0.75 dB per square root hour, with a bias on the order of 1.9 dB per hour. The mechanical thermal noise of the device as this quality factor and mode matched can basically showing that the limit really of the device is one order of magnitude low. So there is a room for improvement to make this device a high performance by an order of magnitude. So this is the conclusion, so several things were demonstrated that we introduced the concept of mode ordering. We showed that basically the concept does work, where we have anti-phase and phase modes separated and ordered, placed in the right order. We achieved the quality factor by design concept close to thermoelastic damping, and we show the device, even in such small volume, can be performed on a very reasonable noise level. And this work was performed, was sponsored by different parts of this work, were supported by DARPA, and at Stanford, the work was supported by the National Federation. Thank you very much.
Thank you very much.